We'll be using chat to answer some questions throughout the presentation. Both Mose and I will be presenting, and so if you have questions about stuff, the person who is not presenting will be able to respond in chat or the Q&A panel. And then we'll have plenty of time for questions afterwards, as this will be a very interactive webinar as best as we can make it.
Yep.
Wow, we got our first binary builder working on this question.
Yes, hard question.
Easy enough. Binary Builder does not work on Windows yet. We have some Docker support and some tar.jl support that is in a imperfect state right now. It probably will work on Windows one day, but not yet. All right, it's 1 past the hour, so I think that we can officially get started. So I'm going to begin the screen share, and we can kick off the presentation. All right, hello everybody, and welcome to our talk. I'm Elliot Saba.
And I'm Mose Giordano.
And we're going to be giving a presentation on BinaryBuilder, a tool that we have built and grown for the Julia community to be able to build binaries that just work. So without further ado, let's dig in. BinaryBuilder is a tool that helps you cross-compile binaries for a large number of systems. This includes every system that Julia itself is officially supported on, whether it be Linux, Mac, Windows, FreeBSD, whether they have ARM processors, whether they have Intel processors. It's going to automatically catch portability issues, and in many cases correct them. Portability issues are things that would stop a binary that works on your system from running on someone else's system, which has been a big issue in the past for distribution of binaries. BinaryBuilder essentially provides an end-to-end solution for building and deploying binaries for packages. So when we say binaries here, we're specifically talking about the third-party binaries that your Julia packages may require in order to run. We're not talking about compiling Julia code itself into binaries. So as a quick tour of the history of binaries in the Julia ecosystem, back in 2013, Kano built this package called Bindeps.jl. And Bindeps provided a way to essentially run a script after a package has been installed. We, for completely arbitrary reasons, called it deps/build.jl. And it was just a Julia script that ran after a pkg.add was done. And Bindeps provided a framework to download and build or just unpack binaries. After Bindeps, we immediately started creating all of these different providers for Bindeps, things like Homebrew or WinRPM. There were APT and Yum-based providers. And this, I'm sorry? Okay. And this was a pretty stable setup for about a few months. But one of the issues is that with these third-party providers, binaries could change out from underneath packages, and this happened quite a bit. Things like Qt or Cairo would change how they were installed, or would change some feature that was needed, or would just plain break. And this would negatively impact the package ecosystem quite a bit. Bindeps also allowed users to download the source and build the source directly on their machine. But of course, if compilers are misconfigured, if you don't have all of the necessary dependencies, the libraries and whatnot, that doesn't work either. And furthermore, downloading things and storing them into your package directory stores mutable state. And if there's anything that we have learned in packaging Julia packages for as many years as we have, it's that mutable state is evil, because an incomplete build can leave a package in an unreconcilable state, at least from an automatic perspective. And so users then have to go in and manually clear out build caches and such. It's not fun. In 2017, we got frustrated with the third-party binary providers. And so we built this thing called, cleverly named Binary Provider. And this basically just streamlined some of the downloading steps from things like Bindeps. It didn't do anything fundamentally different, except that it had no way for people to build from source. The real reason we built Binary Provider, however, was to consume the output of BinaryBuilder. BinaryBuilder was the first attempt of the Julia community to provide a way for other tools that are written in C or C++ or Fortran or Go or Rust to create binaries for the Julia ecosystem on the developer's machine rather than on the user's machine. BinaryBuilder would allow us to create the things that Binary Provider could download. And this worked well for a number of years as well, right up until we introduced a new concept in the package ecosystem called artifacts, and from those made JLL packages. And these JLL packages essentially allowed us to download things at package.add time. JLLs also provide this binary API that allow your packages to make use of the libraries and executables that have been built by BinaryBuilder in a principled and uniform way. And of course, there is the future, which is building more things and loading them quicker. Now, the overall trend across this entire history is that over time, we have attempted to streamline the downloading and unpacking of binaries on the user's machine to the point where less and less work is happening on the user's machine. We started out with compiling the whole thing. Then we moved to using third-party things to download precompiled things. And now finally, we are at a point where the downloading and unpacking is integrated into the package manager. It's very fast, and it's also done in a completely immutable way, such that after something is unpacked, we know that the exact bits on disk are what the package developer intended. We're also been pushing on the idea that, well, yes, it's the same thing, that the packages that are installed are exactly what the package developer intended. Now, I'm going to have to break out of this really quick and adjust my zoom settings because it's been covering the screen. There we go. Let's continue. So the binary builder workflow is that we start out with some source and a recipe. The recipe gives the instructions on how to build the source. We feed that into BinaryBuilder, which has inside of it multiple compiler shards. Compiler shards target different platforms that Julia can run on, such as 32-bit Linux or 64-bit Mac OS or 64-bit Windows, etc. And each of these are going to create binaries in tarball form. Now, the way that BinaryBuilder does this is through providing a build environment that's going to make it easy to target these different platforms. Each target is represented by a collection of cross compilers. So BinaryBuilder itself runs inside essentially a modified Linux. And that modified Linux is going to host the binaries, the compilers that will actually turn the source code into binaries to run on some other platform. Hence, it's cross-compilation instead of native compilation. We have compilers for C, C++, Fortran, Go, Rust, and more. We create one set of output, so one tarball per architecture, operating system, and runtime libraries in all the different ways that they can be incompatible. As an example, when we name the output, it's going to be named something like this, where it says, x86-64, Linux GNU, libg4chan3, cxx11. We call this a platform triplet, even though there are more than 3 terms here. Most other people only use 3 terms, but we keep on adding terms because we keep on finding new ways that binaries can be incompatible. So in this case, x86-64 is the architecture. It means it's a 64-bit Intel processor. The OS is Linux, and the C runtime library is glibc, which is typically announced by this GNU tag at the end of platform triplets. Now, because Julia links against Fortran code by default, and because it links against C++ code by default, there are certain ABIs that are embedded into it that restrict the kinds of libraries that it can load. So we have to record the Fortran and C++ ABIs that are embedded within each build of a dependency so that Julia can load one that is compatible with it. This depends on essentially what Fortran compiler and what C++ compiler you built Julia with in the first place. For most people, if they're using the official julialang.org binaries, this will be constant. But some people don't. They build Julia from source. And so we have to polymorph ourselves to match that, rather than just stating unequivocally that everyone in the ecosystem must use a certain libg Fortran and must use a certain C++ string ABI. Yes, so these are the list of things that can change here, which libc you're using. We also support musl as well as glibc on Linux, and libg Fortran, libstd C++ version, and also the C++ string ABI. Right now, there are about 50 possible permutations if you were to build a binary that depends on Fortran and C++ and has all support for all the platforms, et cetera, et cetera. And it will grow even more. Of course, we do our best to be intelligent about this. If your library doesn't have any Fortran code in it at all, then it doesn't matter what version of Fortran Julia was built with. So we don't have to worry about building different versions for libg Fortran version 3 or version 4 or version 5, etc. So cross compilers are contained within these things called compiler shards, which are basically just a set of compilers and headers and libraries and such that GCC and Clang and such can use to build code for the target platform. We actually have multiple GCC and LLVM versions for each target. So we can do things like we can say, my project requires GCC 6 or newer because I use some fancy C++ features, and I want it to target for Linux with ARM processors and Linux with Intel processors and Mac OS, and that's it. You can do that kind of specification in your binary builder recipe, and it will work. We package every version of GCC from 4 all the way up to 9, and we package every version of LLVM from, I believe it's 7 to 10. So if there are compiler bugs that would affect your ability to build your package, which happens more often than you might think, you can just switch the compiler versions until you find one that works. So the way that we provide this is through containerization. So very similar to how Docker works, we have an execution backend that allows us to build a small little self-contained universe that has exactly the kind of file system that we want to present to the build environment, and that isolates your host computer from influencing the build at all. It's a nice hermetically sealed container within which we can do whatever we want. On Linux, it directly uses user namespaces. This is the fundamental Linux kernel functionality that makes Docker so efficient. On macOS, we actually just use Docker, which is internally using hypervisor.framework that runs the build within a very performant, but still a VM. So it's it's less performant than if you were to run it on Linux. In the future, as we said in that first question before the stream started, we do plan to have Windows support, probably through using Docker. However, it's not working quite yet. And we encourage everyone who is doing a lot of this stuff locally to use Linux, because it will be the highest performance and most commonly used platform. So before continuing, let's explore the build environment just a little bit. If you have BinaryBuilder installed, you can actually get an interactive shell inside of the build environment by using BinaryBuilder.run shell. So we're going to do that, and we're going to poke around a little bit and just see what it looks like from the perspective of the stuff being built. So I will increase the text size here. Let me just double check with my collaborators. Can you guys see the terminal?
Yes.
All right, great. All right. So I have on this computer a directory that has just a single C file. And what I'm going to do is, if I were to just run gcc test.c to compile this C file, what it will create is a binary output that is a 64-bit Linux object. And I can run that on this machine that says, hello, JuliaCon 2020. The C code is not particularly interesting. However, if I wanted to compile this for example, Mac OS, I could enter the binary builder shell. I'll enter the binary builder environment, which I will do through this. Now, if I pass nothing in by default, it will run a environment that matches the one that I'm currently running. But I don't want to do that. I want to run in a Mac OS targeting environment. So I'll pass in a platform object that specifies the target that I want to target, the platform that I want to target. And what happens is I get dropped into a bash shell. And when I look around, I still see test.c and also that test file that I created. However, if I were to remove that binary and compile it again, what I get is a Mach-O 64-bit executable, which is in fact what Mac OS uses. If I were to attempt to run it, that won't work because this is not in fact a Mac OS system. If I ask, what is this? It claims that it is a Darwin system. Of course, it's not. But this environment is going to be doing everything it can to convince the build system running inside of it, like make or CMake or anything like that, that what it's building on is in fact a Mac computer. Now, if I were to say, all right, I used GCC in here and it created a Mach O executable instead of an ELF executable, so it created something for Mac OS instead of Linux. So I may ask myself, well, what is GCC? So if I say, hey, what is GCC? It is located at this place opt bin GCC. And if I take a look at that, it is in fact a symlink that points to a GCC that is prefixed by the target that we are targeting. In this case, 64-bit Apple Intel processor. If I take a look at that file, we see that that is in fact a binary, but it's extremely small. If we take a look at what it is in fact a shell script. And we'll talk a little bit more about this later. But essentially what this is it is a way for us as the binary builder environment to control what kind of flags and what kind of things are being fed to the compilers within this build system. Part of it is to add in flags that need to happen because the binary environment is a little bit weird. It's not the typical environment that most builds around the world are happening in. And other parts of it are things like catching usage of compiler options that we know are suboptimal or that we know will cause problems down the line, etc. All right, let's get back to the presentation. Oh, and of course, if we were to pass a different platform object into that run shell function, then the which compiler excuse me. Then which compiler is used by the build environment would change. So as we saw, the cross compilers that we're using are themselves smart. They're shell scripts that are generated to avoid bad compiler options and add good ones, etc. The cross compilers will automatically use Ccache when appropriate in order to speed up builds. When you're building the same thing 7 times because you keep on running into errors, it's very helpful to have Ccache there to speed up the rote work of compiling dozens of C files. And the environment tells lots of convenient lies. Uname and syscontrol and these kinds of tools are all available so that when a build system tries to introspect and say, all right, what system am I running on? We can tell the appropriate lies so that most things will auto-configure properly. Occasionally, because we're cross-compiling, and not every piece of software has great cross-compilation support, we do have to manually patch things or find the right environment variables to set, etc. But we've built quite a lot of software in this environment so far, and 90% of it requires no special configuration. Now, the output of BinaryBuilder, as said a few slides ago, is tarballs. There'll be the tarballs containing the binaries, the headers, the libraries, etc. Once that output is generated, we do have an auditing step that Mose will talk about more. But this auditing step checks for errors. It checks for things like, can your binaries be relocated properly? Are they going to be able to find all of their dependent libraries on the target system? Is there a dependence on compiler support libraries, things like libg Fortran or libstdc++? Will there be microarchitectural mismatches? Has your build resulted in a binary that uses instructions that may not be available on every user's CPU? That kind of stuff. And as said before, one of the things that we introduced a little over a year ago is JLL packages. These little beauties provide a common interface for loading binaries. So when you are using libraries or using executables, it provides a API for your package to use to be able to find and execute those executables or find and load those libraries. It also provides a space-efficient method of doing this, which we did not have in the past. So previously, if you had 3 different versions of the Cairo package installed, they would each have their own version of Cairo and all of its dependencies built inside of that package directory. Nowadays, the JLL packages allow us to share binaries across all the different packages inside of your depot, which is significantly more space efficient and really makes a difference in shared computing areas. And of course, JLL packages now make it as easy as just doing package.add to get binary dependencies in your project, which we will also demonstrate. Most people, when they're building things with BinaryBuilder, don't spend all their time interacting with it locally, however, because Mose and I have gone through the trouble of setting up this thing called Yggdrasil, which is the community build tree. Now, you have your source, you want to build it by using a recipe and get JLL packages and artifacts out of it. Oh, and you also have some dependencies for your recipe. Things like, you require libz in order to build TensorFlow, for instance. Now, you can do all this locally. However, we have set up a system called Yggdrasil that allows the dependencies in the source to come from the vast unknowable internet. And Yggdrasil will hold the recipes that are created by you, the community, and then it will automatically build and publish those recipes into a GitHub organization called Julia Binary Wrappers, where all of these JLL packages and the built artifacts are stored. We will walk through how to do this in the live demo portion of the segment, which is about to begin. So with that, I'll say, take it away, Mose, and he will be able to walk us through using BinaryBuilder, using Yggdrasil, and all that good stuff.
Yeah, thanks, Elliot. So I just wanted to say, since some people are asking about the hats, so we put the hats because we have these hats in our avatars. So if you know us by the avatars on GitHub, for example, you can recognize us. And yeah, so I will take the screen now. And yes, can you see my screen?
Yep.
Okay, perfect. So I wanted to mention briefly at the beginning that we have also a website for BinaryBuilder. This was set up by Kino a few months ago, and Avik also refreshed the look a few weeks ago. So you can go here and see some of the features that Elliot already mentioned about BinaryBuilder, and you can also see a demo of a building with a wizard, but we will also see this later during the demo that I'm going to start. So let me open the terminal. Okay, so to install.
Real quick, I think if you can actually pull the microphone a little bit farther away from your mouth, you're plenty.
Okay, is it good? Okay.
Great.
Okay, so to install BinaryBuilder, BinaryBuilder is like a usual Julia package. So you can just enter Julia and then enter the package manager with a closed square bracket, and then type add BinaryBuilder with the 2B capital. Press enter. It will download the stuff. I already have on my machine, so I don't need to download again. And then type, as usual, using BinaryBuilder to load it. It will take a few seconds, and that's it. So Elliot already talked about some features of BinaryBuilder. I wanted to show you the list of all supported platforms. So you can use the command supported platforms to get the list automatically. So again, we have Linux with different CPUs and also different C libraries. So both the GNU C library and the Muscle C library, macOS, FreeBSD, and 32 and 64-bit Windows. So again, there was also a question about this in the Q&A. So we use a single environment to build binaries for all these target platforms. So even if Binary Builder doesn't run on Windows, we can build binaries for Windows, so that can be used by Windows user. And this is the great advantage of using Binary Builder, that you have a single environment for everything. And Elliot can tell you how hard it is to maintain several different machines to do native compilation. So I want to enter now again in the shell. Okay. So the argument is simply the name of the platform for which you want to build. I just wanted to show something more, but I think that Elliot showed already most of what I wanted to talk about. So if you notice, here I am in this directory where there is nothing, and this directory is actually this one, this JuliaCon directory that I have on my other shell. So if I create a file here, you will see the file also from the other shell. So this means that we have just mounted this environment in this directory, and so we can just work and also see the content of the directory from the outside, of the build environment. Okay. Okay, so Elliot actually already talked about the compiler. We have GCC or Clang. There are some environment variables, but I will get back to the environment variables later, like CC to indicate the name of the default C compiler, or CXX for the default C++ compiler, and so on. And so all these variables are already predefined in the environment, so you don't have to care. And these are, as Elliot said, these are some variables that are used by the most common build systems. So you don't have to care about this. And Binary Builder is doing its best to pretend that these are the correct tools to use for the build. So how to build? There are two ways to build binaries. I will show you first the wizard, which is probably the nicest one. But there is also another way to build the binaries, and we will get back to that later. So to start the wizard, you can run BinaryBuilder run underscore wizard. Let me do this. Okay, so now we are entering the wizard, which will guide us through the build process. So you get this nice banner. Also information about how to get in contact with us. For example, we are active in the Binary Builder channel on Slack. So if you have any questions, you can reach out us here, or also the repo Binary Builder, and so on. So we want to build this package, which is called libcsv. We don't have this in Yggdrasil, so this will be a first time for Yggdrasil. So let's go through the questions that the wizard is going to ask us. So the first question is for which platforms we want to build. So we have already seen that all supported platforms will be this list. And yeah, we want to try to build for all supported platforms. But anyway, if you want only to target a few operating systems, or just completely select some of these platforms, you also have the option to do the fully custom platform choice. But okay, we will go for the all supported platforms. Next question is, please enter the URL. So I will just use the Git repo URL. So I went here to the repo on GitHub. I copied the URL from this link and paste. Okay. So it cloned the repo, and now it's asking me, yes. So for reproducibility, we will not build for just a generic reference like master. We want to build for a very specific revision, so that if we are going to build again in, I don't know, 2 months, 1 year, we will build the same exact version. So, but actually here, if you want, you can type master, and the wizard will automatically get the Git revision corresponding to master. But this is very important. We are building actually for this specific revision, not for master, because this is like a moving target. Instead, we want a very permanent target. Okay, so additional questions. If we want to download additional sources, no. Note that the N is capital, so this means that this is the default choice, and I can just press enter to say no. Do you require any binary dependencies? Also in this case, the answer is no, but we will see later maybe some cases where we can have multiple sources or multiple dependencies. But for this simple demonstration, we will not use anything like this. So also in this case, no. Okay, so new question is enter the name for the project, and I'm going to call it libcsv. Version number. So usually we want to use the same version number as the upstream project. Unfortunately, this project doesn't have any like standard version number. So like they don't have any release. So what I'm going to do here is to just use 0.0.1, just the smallest version number that we can have. Do you want to customize the set of compilers? So I will answer yes, so we can show you what are the options. So we can say build only for, use only the compilers for C, C++, or Fortran, or also, or instead Go and Rust. So these are all the compilers that we can support. But okay, I'm fine with C, D. And then we can choose also the different versions of GCC that we can use. But the default is 4.8, which will be fine in our case. So I'm going to press enter here, and also the version of LLVM. So you can see here we have a few different options. Also in this case, I'm happy with the default choice, which is 9 in this case, and press enter. So now you can see the first hints about how magical is the wizard. So the wizard already analyzed the content of the repo that it cloned. So it found that if you enter the directory libcsv, so we'll use the command cd libcsv, there is a file called configure. And configure is a standard name for the configuration script used by GNU autoconf. And when we build for a GNU autoconf project, this is what we have to run. So you can see that the wizard is already telling us what to do, and it is literally guiding us through the process of building. So it is suggesting that probably the steps to build will be configure followed by make and make install. We can just double check on the README of this project. The installation steps are actually these ones, so that's fine. So configure, make check, and make install. So just a note, we are going to do cross compilation. So this means that we don't have the possibility to run the compiled binaries or libraries for all the supported platforms. So everything that involves running something built for the target platform is not going to work. So steps like make check, unfortunately, we cannot run them. But okay. So anyway, we can see that the wizard suggested us the right steps to build the library, and this is great. So we can just copy this one, press enter to run the command, and now try to build. So we will build, we can build also in parallel, so using as many cores as our computer has, using this nproc environment variable, which as the it automatically gets the number of processors on the machine. And this fails. So this what happens many times, that you have to like try to figure out what's the problem. So in this case, I know that the problem is that some scripts in these build systems need to be refreshed. So this can be done automatically with autoreconf. We will use some flags. And okay, so we'll try again to configure and to run make. We will see if this works now. Okay. So no error, probably it worked, and we can install the library. That's it, run. Okay, finished. So we can leave the build environment with Control D. And yes, so this is a new feature that Kino introduced a few months ago. So the wizard found that some files changed since we have created the build environment. So this happened because we have run the autoreconf command. So what the wizard is doing is to make a diff between the files that there were at the beginning of the build, when we entered the build environment, and the files at the end. And it found all these differences. So in this case, I'm not interested, just because these files have been automatically regenerated by the autoreconf command. So I don't really need to take care of keeping track of these diffs. So I'm going to answer that no, I don't want to turn these modifications into a patch, so N. But in other cases, this feature is very useful because you can make some small edits to the files in the source of your package to make the compilation successful. And so now a new question. So the wizard kept track of all the commands that I've run since I entered the build environment, and it is asking me whether I am happy with all these steps. So actually I want to make some changes because the first make was unsuccessful. So I had to rerun autoreconf and restart from scratch with configure. So yes, I want to edit the script. So this is VI, so I need to remember how to delete the lines, and it should be double D. Yes. Okay. So this is the build script that I want to run. Just enter into the directory, run autoreconf, run configure, run make, and run make install. So I'm happy. I can exit if I remember how to exit from VI. And yeah, so now since I've changed the build script, it's going to run again the build script to double check that everything is going to work. And it was happy. And so you can see here some steps, additional steps that the wizard is doing. So first of all, it is automatically installing the license. So the wizard has found that there are some files with some sensible names like license or copying, and it's automatically installing them into the target, into the so-called prefix where all the binaries will be installed. And after that, there is the audit. So audit is going to perform some checks, like sanity checks, that everything is fine. So it's going to check the run path of the library, also the name, so the name of the library, which is written inside the library in the header of the library. It's going to check for the license and so on. So this audit will do a lot of checks to make sure that everything is consistent and it is mostly probably going to work. At the end of the build process, it will check also the wizard for the existence of some specific files, like a shared library into the lib directory in the prefix. So it believes that this is like a product that is interesting for our case. And so it is asking us for the name for this product. So this name will be used in the JLL package that we will see later. So I'm going to say, call this product libcsv, so that when I want to refer to this library, I will call it libcsv in the Julia package. So, yes, sorry, probably I didn't mention, at the first time we built for 64 bits Linux environment. So now we are going to try to build for all the other supported platforms, and the next one will be Windows, 64-bit Windows. So this is the CPU, MinGW is the runtime, which is the runtime used for building stuff for Windows. And so yes, we will press enter to continue. So it is going to just repeat the steps in this build script, repeat the same steps for this new platform. So compilation seems to be successful, but there is a problem. So it says that could not find the correspondences for this libcsv file. So apparently it is saying that it cannot find the library where it is supposed to be. So I will enter into the build environment to check what's happening. So this will also give us the opportunity to check how this works. So we can move into the prefix. The prefix is where all the files are installed at the end of the build. So inside this prefix directory, there are 3 directories. So include, where are the header files, and lib. But inside this lib, there are only static archives and a libtool file that we're not interested in. But we are missing the shared library. So shared libraries usually for Windows have extension .dll. And also, usually for Windows, we expect the shared library to be installed on under the bin directory. So here we have 2 problems. There is no bin directory here, and also there is no shared library at all. So when you have problems, my suggestion is to go to BinaryBuilder documentation. So if you go to BinaryBuilder, there is here the link to go to the documentation. I already opened it here. And there is a section for build troubleshooting. So here we have collecting some common problems that we have experienced while building stuff. So you can go through this list. So this problem is happening only on Windows. So maybe we can go to the Windows section to see if there is a problem that is relevant to our case. And there is this section. So libtool refuses to build the shared library because of undefined symbols. So let's double check here in the log of the build. And this is actually our case. So libtool is saying undefined symbols not allowed when building for Windows, when building the shared library for Windows. And so it's building only the static archive, which is in fact what we can see here. So the .a is a static archive. And so the build process only built the static archives. And so yes, here in the in this section of the manual, we have explained how to work around this issue. So here I've written the proper fix, but I'm going to use this quick and dirty solution. So just to pass these extra flags to make. So this basically is going to say to use this non-defined flag for the linker. And so yes, we have seen here the content of the build environment. I'm going to exit with Control D, and I want to edit the build script, so press yes. And I'm going to add here these lines that I've copied, and I'm going to pass to make these new flags. So I can save the build script. And now it's trying to rebuild again using the new build script that I've passed to see if this time is successful. And yeah, so this time, luckily, the informations that were here in the documentation were good enough for our case to fix the build failure. And so now we can go forward with the new platform. So in this case, now we're building for the 64-bit ARM Linux. So press enter, it's going to build. And this one was successful, congratulations. So now we have built for 3 different platforms and they were all successful. So we are now kind of confident that it's going to work for all the other platforms. So from now on, I will press enter and the wizard will not be as verbose as now. So it will just show a line, like building for this platform, and show a tick or a cross, whether the compilation is successful. So it was successful for the first one. So now it's repeating every time the build script that I've created. And it's going on through all the list of supported platforms. Yeah, so far so good. So now it's going to build for the muzzle-based Linux platforms. Yeah, again, I hope that you can appreciate the power of this tool, that from a single environment, from a single machine, you can build the same library with the same build script for 13 different platforms. So this is a really great advantage compared to do like 13 different native compilation on 13 different machines. And okay, yeah, it was successful for all the platforms using this build script. And now it is asking us what we want to do. So we can either print to screen the build script or write to a local file, or we can automatically open a pull request for Yggdrasil. So this is what I want to do. So I can press enter. It is asking me whether I want to just like create a branch and then decide whether to open the pull request or go ahead and open the pull request. I want to open the pull request directly. So I press enter here. So usually it will ask you for the GitHub credentials. If you don't want to use the GitHub to give the wizard the GitHub credentials, you can just write the file locally and open the pull request manually. In my case, I already passed my GitHub credentials, so it doesn't need to enter now during the demo. And that's it. Press enter to exit. So let's now go to Yggdrasil. And yeah, so I already opened automatically. I didn't have to do anything. I already opened this pull request, which created this build script. So this build script, maybe I can show the file. So this build script is just a plain Julia script, which encodes all the informations that we basically have told to the wizard. So like all the platform for which to build, the name of the product, the list of dependencies, which in this case is just an empty vector because we didn't have any dependency. The only source was the Git repository that we used for the build. And then the name of the package and the version number, sorry. And all these informations are then passed to this build tarballs function that will run the compilation. So what's happening now, if I manage to go here, so we have set up a sophisticated CI system based on Azure pipelines, which is building all these libraries for us using a dedicated machine. So what is doing the CI pipeline is to read this file, extract all the relevant information. For example, the list of platforms for which we're building, and it is creating a different job for each platform. So now you can, for example, open this one and check the log. It is just repeating what you've done so far. And that's it. So running also the audit here, all the steps of the audit that we have seen during the wizard. And yeah, so if you want to contribute to Yggdrasil, actually you don't have to run the wizard if you really don't want to. You can just create the build script. We are happy also to take some build scripts that are incomplete, and we can help to fix them, to make them successful. And yeah, so okay, so most of the platforms already finished. Some are green. There are 2 platforms missing. And yeah, let's go back to the, no, sorry, to the pull request. So just waiting for the pull request to finish all the checks. And yeah, so now I can merge this pull request. So what it's doing now is to create a new job in the CI system here, which will do 2 things. It will first create the JLL package under the Julia binary wrappers organization on GitHub. So we will see in a few seconds that it will create the repository. So it will create the repository, skip the build of the binaries because it will just reuse the binaries that is built before. And it will also register this package in the general, in the Julia general registry, so that this will be can be used later as a JLL package that is a plain normal Julia package that can be installed as usual as any Julia package. So, okay, so the first step of this job finished. So just a comment about this CI system. So what this generator step is doing is to check all the files that have been modified by a pull request and only build the package corresponding to those files. So this is really like quite smart because it doesn't have to know. Let me show first actually how Yggdrasil is organized. So Yggdrasil, it has all the build scripts organized alphabetically in this directory. So like libcsv will be in here under L. So libcsv, okay, here it is. So in this directory, you can find this script, build tarballs.jl script. And yeah, so what the CI system is doing is to check that only this file has been touched by the pull request, for example, or the commit to master, and building only this one. So this is how we can automatically detect for which packages and for which platform we have to build. So the JLL package has been created. So if I go to the Julia binary wrappers organization, I can see that there is already the repo here. So now it is uploading all the tarballs that has created. And in a few seconds, yes, it finished to upload, and now it's creating the JLL package. So if I refresh here, yes, here you can see the full Julia package, which is composed of the project file. So with the name, UUD, version number, dependencies, and compat versions. Just a quick note about the compatibility. This is a lie. So actually, these JLL packages will work only with Julia 0.3 and later versions. So this is not actually true, but this is done to make it possible to install the packages also in previous versions, but they will not going to work. Okay, so we have this package, and this is an important ingredient of this package, the artifacts.toml file. So this file records all the information about the tarballs that has been created. So this tarball, let me show the tarballs. They are in the releases that I don't see here. So yeah, it created the release, and it has uploaded as artifacts, as files, all the tarballs into the release page. So you can, for example, download the libcsv for your platform. I don't know, for example, for Windows, 64-bit Windows. You can just download this one. And okay, so this is very small. But okay, this is just a tarball containing all the files that has been created as part of the build process. Okay, so these are the tarballs, and the artifacts.toml file is saying where to find these tarballs. So it's saying for this platform, this CPU, this C library, this operating system, you have to download this file, which has this hash. You don't have to care about this, so this will be done automatically by the package manager in Julia. So when you install this libcsv JLL package in Julia, it will automatically identify your operating system and choose the corresponding JLL package from here and download it, and download the tarball corresponding to your operating system. So yeah, this really streamlines the process of installing the libraries for the users. So they don't have to struggle with, for example, admin permissions to install packages, or go and find the right version of the package, or build the package themselves on the machine. So this is really a very straightforward way to provide the binaries for the users. So, okay, so we also said that this has created, yes, the pull request for the general registry. And also here we have a sophisticated CI automatically. This is all automatic, so we don't have to do anything. So in a few minutes, the pull request will be automatically merged because all is successful. But to make things faster, I will just merge myself this pull request, so that if I go, if I go back to the terminal and update the registry, I can type up libcsv underscore JLL. So I can press enter, and this is downloading. You can see here it is downloading the artifact that has been just created, and I can then run using libcsv JLL, precompiling it, and that's it. So now you can use this variable. If you remember, this is the name that I've been asked to enter corresponding to the product. So I can just type libcsv. And this is what user will use, for example, with ccall. So sorry, now I don't know this library, so I don't know what's the syntax, but let's pretend that there is a function called, I don't know, read CSV, libcsv, which is, I don't know, void type, and takes a string as input. And the string is like the path to the CSV file. So I'm just making up this syntax. I really don't know how this library works, but this is just to show how the user will be able to use this library. So this variable is what is to be used as the name of the library here in the CC. Finding the library, or finding the library, or opening the library, or whatever. Yeah, so I think that this is most of what I wanted to show at the beginning. I don't know if there are some questions at this point.
Yeah, let's take a little bit of time to see if there are any questions, because that's a lot of material that we just went over. Everybody go ahead and take a drink of water. All right, if there are no burning questions, then I will go ahead and switch back to my PowerPoint and talk a little bit about some of the future stuff. We did get one question from Marcus. I'll answer this live. The question is, how reproducible are the resulting tarballs? Are they bit by bit identical each time? What a great question. Yep. So these tarballs are not bit for bit identical each time. However, we continue to make progress towards that. It's a little tricky because there's a lot of things that can influence a tarball, as the Debian guys can for sure tell you, because there are an incredible number of things that they have had to do in order to get reproducible builds. We are, shall we say, halfway there, in that we have complete control over the file system. We have complete control over the build environment, but there are some things that we do not yet exert control over. One example is time. So if the build script, for instance, calls the current time and embeds a timestamp into a file, we give the current timestamp, and that will, of course, change over time, tautologically. The issue there is that in order to do that, we would have to hook into whatever method that they are using to tell the current time, and that's not high on our priority list. We would like to be able to do that eventually, to have completely reproducible builds, but we have other things that we're pushing on first. If you are interested in adding that kind of stuff to the BinaryBuilder environment, we'd be happy to code review, mentor, all that kind of stuff.
Yeah, I just wanted to add that probably making the tarball, the entire tarball reproducible bit by bit is very hard, because there is also the log that can, for example, be affected by parallel execution. But the library and the executable might be easier to get them reproducible.
That's true. And that's really what we care about.
Yeah. Yeah, more than the entire tarball, more the products. there is another question by Eric, which probably you're going to ask in the presentation.
I'll take that one. And then you can take the one underneath it. So Eric, does adding a new supported platform require updates to Julia since the platform information is in artifacts.toml? Yes. Well, yes and no, but mostly yes. As an example, we want to add ARM version 6 support. And in order to do that, we need PKG to know what ARM version 6 is in order to pull the correct entry out of that artifacts.toml file. We had the foresight to add ARM version 6 before we had BinaryBuilder support for it. So we still are working on the ARM version 6 BinaryBuilder support, but package has been able to deal with that since, I believe, Julia version 1.4. However, an example of where we have not had that fantastic foresight is with the microarchitecture specific builds that we'll be talking about in a little bit. And so here we actually have BinaryBuilder support before package had the ability to recognize the platforms that are sharded not only by architecture, but also microarchitecture. We do have plans to make the format that Julia and package use to look inside that TOML file a little bit more extensible so that we won't have to deal with this lagging support in Julia quite so much, but it's not merged yet. Hopefully by 1.6, we will have what we call extendable platform support that will allow us to have kind of user-defined tags that can be used to pull artifacts out so that we can deal with things like microarchitectures or CUDA versions, that kind of stuff.
Yes, so there is a question about if you want to build for macOS using, for example, GCC instead of LLVM. So the answer is yes, it is possible, and I'm sending the link to the documentation explaining how to do that. So yeah, have a look at the documentation. So I think that now we have quite some information that you can find already if you have some problems, but feel free to ask any other question if you have. Oh, wow, so many questions.
For those who don't want to go and find the link for the documentation, it often really is just as easy as just calling GCC or Clang. We provide links for both. We provide a symlinks for both. Okay, to make a package depending on artifacts that do not need to be built, say text files, should one create a package with an artifacts.toml manually or create a JLL through BinaryBuilder? What a great question.
Yes.
From a technical perspective, there's not that big of a difference. The JLL package is basically just a Julia wrapper around artifacts. You can, of course, create an artifacts.toml file manually and download the artifacts directly in your Julia package. So for instance, say you have a foo.jl, and then you have like a foo.jl, then you have a foo.jll.jl that you create to wrap around whatever files you need. The real magic that's in the JLL files is the fact that they are created by BinaryBuilder. They have one per every platform, et cetera, et cetera. So if you have something, like he says, text files, you don't really need most of that. Now, the big differentiator would be if these text files need to be consumed by some other recipe that is inside of the build tree, that's inside of Yggdrasil, then it should definitely be done through a BinaryBuilder script that generates a JLL package. The reason being, because then they can be listed as dependencies for other things that are being built. If you don't intend to do that, if this is just for your particular package, then there's really no benefit to doing it through BinaryBuilder and creating a JLL package. There is in fact a very minor downside to it, which is that you have just yet one more package to load, which will increase your overall package load time by just a little bit. So I would suggest creating an artifacts.toml file manually if these text files do not need to be consumed by any other build recipes.
Okay, so now there is a question about commercial applications. So I'm not going to show probably how to do this locally. So, okay, sorry, let me read the question. So will you demonstrate the workflow for this? So the wizard is not going to work because okay, so the question is more if you have something local, right? Because there is also a question in the chat. I'm trying to merge two different questions because there was a question in the chat whether you can use like local repositories, and the answer is yes. You will just not publish to Yggdrasil. But I will probably show you how to build something using something local. But the question in the Q&A by Rick, so you can use the same workflow, yes. And again, also in this case, probably you don't want to publish to Yggdrasil, but just build the tarballs locally and distribute to your users. So I hope that I answered the question.
I have another thing to add to that. So assuming you have a GitHub repository, but the GitHub repository is private, if that is the case, then some of our tooling won't work necessarily that well. So things like Yggdrasil, etc., of course, that obviously will not work because it will not be publicly available. However, if you have the ability to set things like GitHub tokens in your shell environment, then BinaryBuilder can use things like libgit to fetch source archives from your private GitHub repository, and then it can build them. It can build all the tarballs and such locally, and then you can have it deploy to a private JLL package inside your own user account. Now, we don't have built-in support for this, so you would have to do things like create the private JLL package first and set it to be private, because otherwise BinaryBuilder will automatically open a public JLL package, which would be bad because we don't want the outside world to be able to download your precious binaries. And so if you do that first, then it can deploy things automatically to your private JLL package. Then you can yourself manually register that JLL package to your own private registry. And then you would have your own completely self-contained binary package. As a general rule of thumb, the tooling for open source projects is generally better than that for commercial projects when you're dealing with all the free Julia stuff. For the commercial side of things, there's an actual product called Julia Team, which has better support for this kind of stuff. So if you want a better experience with that, I suggest you get in contact with the Julia Team people who will be very happy to talk us over with you at the Julia Computing organization.
Okay. So now another hard question. Do you support MS Visual Studio Compiler? The answer is no.
Yeah, that's not so hard. No, we don't.
Yeah, we can only use MinGW.
Right. The reason is pretty straightforward because we need to be able to run this on Linux, and Visual Studio doesn't run on Linux, sadly. In practice, this doesn't really matter for C code because C code, the ABI, is similar enough that MinGW can create MSVC compatible code. For C++, it's a little bit more of a guessing game. It may work, it may not. Our unfortunate reality is that if you are loading C++ code that's built by Microsoft Visual Studio, it may not work in the Julia world. And if we are building stuff from BinaryBuilder to be used by MSVC code on Windows, it may not work. Luckily, Julia itself, I don't think has been buildable by Visual Studio for a while. So this probably won't hurt you if you're living in the Julia ecosystem. However, if you try and use BinaryBuilder built stuff outside of the Julia ecosystem on Windows, it may hurt you.
Okay, so now there is a question. When we add this JLL in our package project toml, okay, can we have a mixture of JLL and older type? Okay, that's a great question. And other older type dependencies. So I can show you. Let me share the screen again, because we have some cases like this. Can you see the screen?
Yep.
Okay, so if you go to Yggdrasil and go to the README, it explains first how to contribute. So if you want to contribute new recipes, you can see here, or just update the version of an existing builder, and also use these generated tarballs. And you can do this in two ways: the JLL packages, which is the most straightforward, but it is only compatible with Julia 1.3, or using binary provider, which is the old way to that Elliot mentioned during this presentation. So if you go to the end, so here says how to generate the scripts that can be provided to binary provided. But you can see here an example of package that is mixing these two ways. So this is done by Jacob, who's doing the other workshop, parallel workshop. So you can see here in the build in the deps slash build.jl file, there is this kind of complicated file which try and guess whether you're using the Julia, an old version of Julia. It will use binary provider. Otherwise, it will just use the JLL package. And the reason to do this is, to be able to use the same tarballs, but provided in two different ways for all the versions of Julia. And this is also why we allow installing the JLL packages in all versions of Julia to make this possible. So if you go to the project.toml, you can see here like this JLL package, MariaDB connector C JLL. This will be installed, the package will be installed every time, but in all versions of Julia, but only will be actually used only with Julia 1.3. So if you want to see again, go to Yggdrasil, to the documentation, and see the last section of the README. It will explain how to do this.
All right. Jeffrey asked a question where he said, is there a path that would allow the JLL process to provide some callable Julia functions to access whatever may be straightforward to do automagically? And he followed that up with a clarification that says, consider a well-designed C library, one where the design is in accord with general flow and organization that works reasonably when seen from Julia. So I think what you're asking is if it's simple enough to look at a C library and see what functions it exports, can we automatically create an API where you just call a Julia function and it does all of the C call magic for you? And unfortunately, this is a little bit beyond what BinaryBuilder is trying to do. There are other projects that attempt to do this, things like clang.jl or cxxwrap.jl. And these help to automatically create these kinds of language bindings. So they can do things like analyze the C code and try and see, oh, okay, this function is expecting to receive a string and an int and an object. And so I'll create a similar function signature in Julia in order to try and call that, that object inside the library. But that's a little out of scope of BinaryBuilder. So I suggest that you take a look at those packages and see if they can get you a little bit closer to what you're looking for. All right. One more question. Today I installed CXXWrap. It seems an artifact and it fails to link using GCC, which says undefined symbols for architecture x86-64. When I download it and build it manually using GC, it works. So my question is really, can users select which version binary to install in the artifacts? I think so when choosing which version of binary to download and install in artifacts, the user can't really influence that because it's not much of a choice. It's going to choose the one that best fits your platform. And in the vast majority of cases, there's only one that will work at all. It sounds to me like you have a different issue. It sounds to me like there's some build that's going wonky and it's failing. I suggest you open an issue either on the CXX wrap repository or on BinaryBuilder if this is trying to build something using BinaryBuilder. Feel free to ping me or the CXX wrap maintainer to get some eyes on it, and we'll try and take a look at that and see what's going wrong.
Yeah.
All right, I'm going to screen share.
Okay.
And we're going to talk a little bit about the future, what's coming up next, all that good stuff. Let's close this Q&A window. There we go. All right. So in the future, we will have microarchitecture specific builds, faster loading JLLs, and partial artifacts. These are the three next steps for BinaryBuilder as we see. Obviously excluding things like greater platform support and things like that. But those don't lend themselves to nicely alliterated titles. So Mosaic, over the past couple months, has been working on a extension to the BinaryBuilder system to allow building artifacts for specific microarchitectures. A microarchitecture is things like the extra instructions that come in newer Intel processors, things like AVX, AVX2, AVX512. On 64-bit ARM, there's different generations like the Thunder X2 and Carmel CPU types. We call them by their names because it's not as exciting to say ARM v8.2 or ARM v8.3. And of course, on ARM version 7, we have things like the floating point extensions, Neon for SIMD, etc. Now, allowing the BinaryBuilder compiler shards to generate specific outputs that include these instructions means that in the worst case, if we have a package that links against libg Fortran that uses a string ABI that the C++ that requires us to split on C++ string ABI and uses all of these different microarchitectures, it means that for a single recipe, we may have over 200 individual builds, which is why we call this microarchitectural madness. However, in some cases, this may be very beneficial. Some libraries, especially ones that come from the HPC world, already have inside of them code to inspect the current CPU that it's running on and use optimized versions of its functions for that particular CPU type. Others do not, and those others are where this kind of technology would be useful. It's able to take just a plain old library and turn it into something that will be optimized for a particular CPU type. Now, as mentioned earlier, this will require future package capabilities because we do not yet have the expressiveness in package to figure out what kind of CPU type the current machine is running and download the appropriate artifact. We can do this for what are called lazy artifacts, artifacts that are not installed at package.add time, but that are instead installed at runtime. That is not the greatest user experience. It means that there's a little bit more time the very first time you run it required before you can get to doing your work. But it is something that we're working on merging in for Julia 1.6. The next piece is for speeding up JLL package load time. So for those of you that were perfectly happy before we had JLL packages at all, you had a system that things worked on, first off, lucky you. But secondly, you noticed that when we moved to JLL packages, loading of libraries suddenly got a lot slower. And there are many reasons for this, and we've addressed some of those reasons and won back some of the performance. But there's still a pretty big performance gap. And one of the reasons for this is that libraries are not loaded lazily, they're loaded eagerly. The reason for this is because when we have libraries that depend on other libraries, because the libraries aren't located right next to each other, they have a hard time finding their dependencies. And so we eagerly load everything so that all dependencies are already loaded whenever we are to load a new library. As an example, when I'm using 0mq and I want to call a function inside of libzmq, I'll do it with syntax like this. And this libzmq object here, it's just a string that says like libzmq.so. And ccall is able to find lib0mq because it's already loaded. It already knows where it is. libzmq is able to find all of its dependencies because inside of every JLL package in the init function, we have DL opens that load all of the libraries that are exposed by that JLL package. This means that every time you load a JLL package, it's immediately, eagerly DL opening all of the libraries inside of that package. This is somewhat wasteful sometimes because there may be packages that have many dozens of libraries, and you actually only need to open half of them. But there's no way for the program to know what you're going to call in the future, so it just loads everything. Our proposed change is to change the API contract of JLL packages to, instead of exposing a constant string for users to use in their ccalls, it instead has a function. And this function will then lazily open all of the recursive dependencies that libzmq needs in order to have it load properly. This will push some of the time required before you can use functions from init time to first call time. So in that sense, it won't be saving any effort. However, if you never use some libraries, it's going to save that time that would be spent opening them completely. This is contingent on a little bit of compiler work from the Julia side, because so far you can't pass non-constant expressions into ccalls like this. However, we've talked with the compiler team, and we think we'll be able to get this in for 1.6 to be able to have ccall deal with dynamic library names like this. Finally, partial artifacts. I'm really stretching the alliterative titles here, but we do what we must. So sometimes we don't want to ship an entire build output. So as you saw when Mosé downloaded that tarball, and there were configuration files, there were header files, there were static libraries, dynamic libraries. From the perspective of Julia, from your Julia package, when you're using a library, you don't actually care about most of that other stuff. A C compiler might care. A C compiler needs those headers to know what's inside of the dynamic library. But from a Julia perspective, you often don't need those. So it would be nice if we didn't have to ship that entire tarball every single time to all consumers of the package. It would be nice if, for instance, when BinaryBuilder needs to fetch a dependency, it can fetch the headers and the libraries. But when just your Julia package needs to fetch the dependency, it gets just the libraries. Another big example is debug symbols. We can split out debug symbols from your libraries, but then if something goes wrong, it would be nice to be able to get those debug symbols back. So one solution to this is we could create even more tarballs. For every build that we do, we could split this up into a minimal, a full plus debug, etc. Imagine the explosion. We could have 600 tarballs for just a single dependency. Glorious. Or we could come up with a way to serve partial artifacts. So there is a proposal open right now on PKG that I have yet to implement, but the idea is essentially a way to have the package client ask for only a subset of what is inside of an artifact, and then be able to kind of upgrade that subset by adding more and more pieces of the original artifact, all the way up until, of course, you have the entire artifact available. This would allow us to give an API where by default, a JLL package could fetch only the bare minimum that it requires. But then if necessary, if say you're trying to debug something, you could do something like say, hey, JLL package, give me the debug symbols as well. And it will download and place those in the appropriate location right next to the rest of the binaries that are already downloaded. And of course, when BinaryBuilder is building something, it would fetch the entire thing, because at build time, the C compiler or any other compiler may need a lot of other things, so it can do that, that eagerly as well. We expect that this would give some modest savings on package download, wait, and install time. But more importantly, it would make it easier to debug and deal with issues in the ecosystem. And that is the end of our presentation. When we first envisioned this workshop, we intended for this to be a very interactive affair, where you guys, now that you have heard the good news of BinaryBuilder and are ready and excited to build your own libraries, that we would be able to walk around and help you guys deal with issues with BinaryBuilder on your local machines, walk you through putting your stuff up onto Yggdrasil, etc. We would still like to do that. So what we would like to do now is open it up to questions again and encourage you all to try and build whatever pieces of infrastructure your packages are lacking. And we'll sit here kind of like TAs at office hours, ready and willing to help you guys with any issues that you may run into. So with that, we'll open it up to Q&A again, and we'll encourage you guys to try and deal with any kinds of issues that you're having in your binary builder scripts.
So I may be able to do another short demo about how to manually create the build script, and also show how to use local files, which probably can be interesting for some people, since there were some questions already about the local files.
That's a great idea.
Okay, so there is already a question, and that probably you can answer.
Yeah, this is another easy one. No, BinaryBuilder does not support RISC-V. Very simple reason why. Julia itself doesn't support RISC-V. Once we get closer to that, then maybe we'll look into BinaryBuilder. Well, of course we will, because we want BinaryBuilder and Julia to be in lockstep.
Yep. Okay, so a question from Matthew that probably I'm going to answer like live now. This is basically what I wanted to show. So, so I believe that the wizard is very nice to get started with BinaryBuilder, but it's, in my opinion, not the best way to use it, because it's not as flexible as possible. So you can do whatever you want with BinaryBuilder by just manually writing or editing the build script. So let me share again the screen. So for example, now I want to try and build libcsv manually, starting from an existing build tarballs file. So what I will do is to go to an existing recipe, like I want to use wget in this case, because also wget uses autoconf. So what I will do here is to just copy this file to libcsv build tarballs.jl. Just a second, because this is on a SSH machine. Okay. So I have this file, but now this is for wget. I want to transform it to build for libcsv, as we have seen before. So I would change here libcsv. The version number was 0.0.1. And so now the sources. Okay, so now it's a good occasion to go to the documentation and see the build packages section. Can you see the documentation? Is it large enough? I take it as a yes. Okay, so if you go to the sources section, you can see that we can use a source this kind of stuff. So archives that are remote files, like a tarball that you can download from the web. Git source is a repository. File source is another remote file that will be downloaded from the internet. And directory source is just a local directory. So honestly, I'm not sure that we can use Git source for local repository. We never tried, but maybe it works. I don't know if you ever tried, Elliot. But okay, if you want to build for local files, I will just suggest to use a directory source. So you pass the path to the directory that you want to use a source and just use it. So for the people asking questions about the building local stuff, this is what you want to use, the directory source. But the rest of the workflow is basically the same. Okay, so now in the case of libcsv, I want to use a git source. I will go again to the website, which was this one. Copy the URL of the git repository and the revision, the hash of the revision, like this one. So the second argument of this git source function is the revision, the git revision of the repository. And then this will be libcsv, and I will just trust that this script will work. No, I want to change, instead of platforms, I will use supported platforms. The products, I know that it's on libcsv, that will be called libcsv. And I'm not going to use any external dependency. Okay. So this is literally what I do most of the time. I just start from an existing recipe and try and guess what are the changes that I need to do to make it work. So then I go to the terminal. So I go to Yggdrasil, libcsv, oops, libc. Okay, so I have this script. So this is a Julia script that you can run with Julia build tarballs, and you also get an help. So if you just pass the help flags, dash help, you will see here some in a few seconds. The help about what are the flags that you can use, the flags or the arguments that you can use. Wonderful, it is rebuilding binary builder. So it will take a few seconds more. But yeah, in a few moments you will be able to see the list of the arguments and the options. Oh, okay, there we go. So this is the usage of the script. The list of targets. If you want the help flag, verbose, debug. So verbose, it shows a lot of verbose log during the build. Debug is very useful. So when there is a failure during the build, you will enter into the build environment, and you will see this later. So these three options are probably interesting for people that want to deploy the JLL package, not to the general, not to Yggdrasil, but to their own GitHub repository. So you can use these options to build to install the JLL somewhere else. And it is also the option to register automatically for the general registry, but this is probably not very interesting if you don't want to register to the general registry. And this other option, meta.json, is to create a JSON file that collects all the information about the build. Okay, so now I'm going to run again this script using these flags, debug, verbose. So without any arguments, it will try to build for all the platforms specified here. But instead, I want to try first to build only for the 64-bit Linux. So there is the triplet function here that you can use applied to the supported platform functions to get the triplet that mentioned, explained before, of all the platforms. So I want to use in particular this one. So that this will be the last argument of my call. So I'm going to run with debug verbose for this platform. So if everything goes fine, it will just work. Otherwise, I will need to fix something. And if it fails, I will enter into the build environment. And this is what happened. But we know already what we have to do. So yeah, when it is trying to run the make command, it cannot find some functions. So we need to run autoreconf like this. And then run again configure. And then run again make. And then run again make install. So just remember that using this workflow, you are not recording anywhere the new commands that you have typed. So you need to remember what are the steps that you have used to make the build successful. So in this case, I remember that I need to run this command. So I will copy and paste to the build script. So I will save the file, exit from here, and try again.
Hey, Mose, one thing that Martin points out is that you still have it listed as a executable dependent, or an executable product rather than a library product.
Oh, okay. No, so now it's going to fail. Yeah.
Yeah, I think it will catch this during the audit pass.
Yes. Yeah. Perfect. So yes, for example, now the audit found that this file that I've declared as executable product is not actually, so executable product is like a program that you can run, so not really a library. So the audit found this inconsistency. It's complaining, and yeah, so the message is this one, that cannot continue without with unsatisfied products. But yeah, we have a very good attendees that are suggesting us what we have to do. If I can type library product, so I can fix again the script, try again to build.
This is another reason why we are so happy to have Ccache be getting automatically and transparently used, because we do this a lot when we are trying to fix build problems. We run it over and over and over again. And some things can be cached, some things can't, but anything that can be cached is nice. So the C build is actually almost instantaneous here.
Yeah. So, okay, now everything was fine, but I've built only for a single platform. So let me try for Windows, because we know that it's going to fail for Windows. So now again, it is going to fail during the build. So we will enter again into the build environment. No, sorry, this is not going to fail during the build, because the build will be successful, but yeah. the product is missing. So what I will do here is to add a command at the end of the build script to make the build fail. So like a false, which return 1. So I will do this. So now I'm literally showing you what I do to debug some failing builds. Oh, by the way, the build is happening in a directory which is under this directory. So if you go like in this build, there is the x86-64 min.gw directory. You can enter here. So the latest one is this one. I can enter. So this is the content of the environment. So what you see in the root, not the root, sorry, in the workspace, yeah, is the content of the directory which is below the build script. So this is very inconvenient for me because I can watch the content of the build environment, but outside of the build environment. Okay, so this is just another trick to keep in mind, that you can follow what's happening from the outside also. So as we have done before, we can go to the to the prefix. I cannot type. Prefix, we realized that the bin directory is not here, so there is only the static archive here, but we know already what we have to do to fix this one. So we will go to the documentation. It was troubleshooting. So I'll go to the documentation, copy this, and just add these steps to the build. Okay, so now I will try again. So this workflow, you can see, requires a lot of more manual work. So it's not as nice as the wizard that keeps tracks of all the commands that you have to run. But in this way, you have much more control. So in the end, this is what I use most of the time. And yeah, so this is successful. So for example, now I could run this without arguments to build for all the platforms, but okay, I'm not going to do this. But I wanted to take the time, if there are no other questions, I don't know if there are questions already. I wanted to go to the documentation to just go through some details of the build script. So you can find already this information in the documentation of the binary builder. So the ingredients, as we have seen, are the name, the version number, the different sources that you can use, archive, git, file, or a local directory. And you can also use multiple sources in the same recipe. So for example, this one, yeah, this libftd2xx is using a lot of different sources like archive, a lot of files, or local directory. We use the local directory most of the time to, okay, no, this is not the case. But in many cases, we use the local directory, so the directory source to keep the patches that we have to apply during the build. So I don't know if you remember quickly a recipe which uses some patches.
Oh yeah, GCC. Although that one's a little obfuscated.
Yeah, maybe OpenBlast, it's easier.
Yeah, OpenBlast is a good one.
So you can see, okay, let me go back to the, so this is the build tarball. Okay, so this is not a good example anyway. So you can go into the bundled/patches directory, and here you can find the patches that then you will need to apply manually during the build.
And as we saw before when Mose was demonstrating the wizard can generate these patches for you automatically. If during your interactive build in the wizard, you edit some of the source files, it will detect that and it will actually offer to create these patches for you automatically.
Yeah, otherwise, if you use this other workflow that I showed before, you have to create the patch yourself and put into the directory yourself. So this really requires a lot of more work, but once you are used, it's fine. But yeah. So the build script is just a simple bash script, because remember, we just use a single, it's like an Alpine Linux environment to build for all the different platforms using a cross compilation. So you list the platforms as a vector, and if you're confident that this is going to work for all the platforms, you can just use this function. Otherwise, you can list in the vector only the platforms that you are interested in. You can get the triplet using the triplet function. And yeah, here you also mentioned that sometimes you need to build for different C++ string APIs or different Fortran versions because of the incompatibilities that Elliot mentioned before. So in this case, you will need to use these functions to say build for what is it? For this string API, C++ string API, and this one. But a very important thing is that the audit will inform you if you need to. So what I do most of the time, and it's also mentioned here. So the first time that I try to build, I just build normally without doing adding these extra functions. I just try to build normally, and the audit will tell me if I need to do something else, if I need to add these extra functions to build for different strings API or Fortran versions. So really, in general, just rely on the audit. Just trust the audit, and it will be fine. I'm skipping that one. Okay, so we have different kind of products that we support. So we have the library that we have already seen, the executable. As I told you before, it's just a program that you can run. A framework is a very recent product that it's only relevant for macOS. So it is a macOS framework. And file product is anything else. So any other kind of files that is not any of the three above.
Importantly, I want to point out that the products that you list here, they are going to influence how the JLL package gets generated. And so for executable products, the API that it presents to your Julia package will be different than for a library product.
Yeah, and if you want to know more about JLL packages, there is a section in the BinaryBuilder documentation which tells you about the structure of the JLL packages and also the API. So what are all the variables that you will find, and how to use the library, how to use the executable, how to use the file product. But this is just a path to the file. So the file product is not very special, but it's sometimes useful to have a file to reference. But yeah, you can find all this information in the documentation of BinaryBuilder. And thanks for pointing this out. So products, binary dependencies. So sometimes you need to have some other packages to use for the build. So it can be other libraries or only the headers of some other libraries, which is the case, for example, of libx11. So in this recipe, we are building libx11. And in the list of dependencies, you can find 2 libraries that are mentioned as dependency. and two other packages, JLL packages, that are called build dependency. So the difference is only for the JLL package, because this will be all installed when you build this package, this library, this libx11 package. But the JLL package will only depend on these ones, on these two packages. It will not depend on these ones because these are build-only dependencies. These are not runtime dependencies. The advantage of specifying the build dependencies is that you will not install these packages when you in Julia. When you install libx11 JLL, you will not install these packages because you don't need them at runtime. So this is a way to distinguish runtime dependencies and build time dependencies.
As a quick aside, anybody who wants to get an easy first PR merged on the BinaryBuilder repo, you can see that in that section that we were just looking at, the binary dependencies section, if you can scroll back down there, Mose, there is a mismatched quote and closing parentheses in this code section. So if you want an easily merged PR, go ahead and go there and fix this piece of documentation.
Yeah, and if you don't know how to modify this, there is the edit on GitHub button here at the top of the file. So you can go here and use the GitHub interface to fix it. So go ahead.
So Matthew has an interesting question.
Okay.
Because I think you've gone through everything in this build tarballs.jl file, Mose. He says, how can we specify the minimal CMake version to be compatible with the requirements of a CMake built project? This is an interesting question because the build environment does provide many build tools. And in some cases, we provide multiple versions. As we said before, we can specify the GCC or LLVM version. In fact, we may want to show how to do that. But CMake is not one of those things that we provide multiple versions for. And in fact, CMake isn't really something we're that concerned about. The reason being because we don't have to build it ourselves. We can just use the CMake that comes in the Alpine Linux environment that we're running inside of. The reason we don't care that much is because nothing about CMake needs to change depending on which target we are building for. CMake is a completely build time tool, and it works for no matter what target we're targeting. The same could be said for instance, if you needed Python during your build script. You can get these tools by just using the built-in APK tool, like the APK package manager, built into Alpine Linux. I'm going to share my screen really quick to show what I mean. So once again, I have this. Shell. Go ahead and just run shell here to get into a build environment. And what I'm going to do is I'm going to see if CMake is installed, and then we're going to see if there's actually a newer version that's available. So is CMake installed? Yes, it is. We happen to have version 3.13 installed. That's what's shipping in the root file system that BinaryBuilder is using by default, which is based off of Alpine. If I were to tell APK to add CMake, let's see what happens. So it says, looks like it's already installed. I wonder if there's an upgrade flag that I can pass here. I don't actually know. There is. And it says it upgraded a bunch of other things, but not CMake, because I guess it's already the latest version that Alpine supports. So if you actually needed a newer version of CMake, you would need to find some way that you can download and run it inside of this environment, which is actually totally possible. So this environment can run most Intel 64 binaries, even if they use glibc or musl, it can run all of that. So if you have a binary that you need to run during your build that's not already provided, you can actually just like curl it and download and run it. or you can include it as a dependency or as a source. There's all sorts of ways to get the binaries that you need for your build. In general, we try to have the latest versions of tools available. So for instance, CMake 3.13 is pretty recent. I believe there is a 3.14 at least that exists that's newer than this.
I
so
think
if you're really
the latest is 17.
Oh, it's up to 17? Fantastic. Time flies. Yeah, you can get it pretty much any way that you want. We may encourage you to do it in a way that is easily reproducible so that it continues to work across time. But yeah, feel free to get any build tools that you need any way that you need to. There is actually one other thing that I wanted to showcase. Yep. There were some questions about doing things locally, especially dealing with JLL packages locally. Mm-hmm. Now, unfortunately, we don't have perfect tooling for being able to, for instance, just build a JLL package locally. It's possible, we do it in Yggdrasil and such, but we don't have an easy function or an easy flag that you can pass to build tarballs.jl. There has been some talk before about adding a deploy local flag to do this, and we would be happy to do that. As Mose showed earlier, we can run the build tarballs.jl file and pass in flags like verbose and debug. We can pass in the platform that we want to build for. What I'm also going to pass in is a flag called deploy. And deploy is going to tell it, hey, instead of uploading the result to, say, the Julia binary wrappers repository or organization, I want you to upload it to my own personal one. So I'm going to do this real quick. It's going to build for only a single platform. It will deploy a JLL package that has an artifact only for that single platform. That's fine. You can see that it says, okay, I'm going to build and deploy version this to staticfloat/libcsv.jll. You can see that it actually has a +1 because it knows in the registry there's already a +0. So it knows that this must be a newer version than what's already in the registry. It goes, it runs the build, just as we've seen a couple times already. And when it's done, it's going to successfully build the artifact and everything. And then it says, all right, I'm committing and pushing libcsv_JLL version that. And it actually does generate it locally. So even though it's pushed it up to the, GitHub, the repository is actually available locally. So if I come over here and I go into my .julia dev directory, there is a libcsv_JLL sitting in here. And if we look around, it has everything we would expect. It has an artifacts.toml that points to that tarball we just uploaded. It has a source directory and such. And if I were to start Julia with the current project in this directory, so I'm using the libcsv.jl and I use it, it'll precompile it, load it, and then I can immediately, just say libcsv.jll.libcsv. It's there. I can see, are you loaded? And the answer is yes, and the file is right here. You'll notice that I didn't even have to download any artifacts. And the reason is because since it was built locally, that artifact already exists on my computer. So the only step that we're really missing here for a truly do everything locally, don't ever upload anything to GitHub, etc. The only thing we're missing is the ability for this step here, when we call the build tarballs, instead of saying deploy equals, for instance, staticfloat/libcsv.jll, instead we need a way to say deploy equals local or something. And so it will only write it out to the file system and it won't attempt to upload anything anywhere. Mose, you want to take the next question?
Yes. have you ever had name clashes in binaries or libraries? So I don't know if the question is more about the package. So in the name of the package, I guess so far, no. But how to handle the situation is to convince the second contributor to slightly change the name, probably.
In terms of libraries, it's pretty rare because most computer systems can't load the same name twice. There's this thing called an SO name, or on macOS, it's called a dylib identifier. And if those are the same, then the operating system will refuse to load the second one because it will say, no, I already have that library loaded. So most people are already solving this namespacing issue for us by just naming everything somewhat uniquely.
Yeah. I mean, it's in the interest of the projects to avoid clashes. So yeah, usually we don't have this problem.
Kind of similar to how we don't have that many name clashes in Julia packages either, because if you want to be able to use a globally identifiable name for your package, it has to be unique. It is possible to have two packages names different things in different registries and whatnot, but using them from the same package, again, technically possible, but challenging. So most people avoid it.
So if we have some more time, I will go through some more sections of the documentation, also to show something else in the build environment. So I'm taking back the screen. Okay, so now I am in the build tips section of the documentation, which explains how to build the packages in different cases. So for example, this showcase the standard way to build packages that use autoconfigure. Also with a couple of examples of recipes in Yggdrasil using it, or also CMake. When you build for CMake, you have to specify the so-called toolchain file, which has all the information about the target platform and what are the tools to use for the target platforms and whatnot. And also another important flag to pass is the CMake build type release, which says optimize this as much as possible. So usually you don't want debug symbols or use a high optimization like -03 or -02. And again, always install the result into the prefix. So this is another important flag to pass to CMake. And then the rest of the build is just as autoconfigure, so make install. We also support Meson, another system to automatically generate the build scripts. In this case, the only flag that you have to pass is cross-file, and we have already prepared file for Meson, which is similar to the toolchain file for CMake. But in this case, you will use Ninja to build instead of Make. But the workflow is similar to CMake. So here says if you want to edit files into the wizard. Actually, this is not up to date because it doesn't mention, I think, the fact that the wizard is able to automatically generate the patch for you. So this is saying that you can edit the file, you need to prepare the patch and add it as a bundled directory source. Yeah, maybe someone should update this section to mention that the wizard is able to do it. Okay, so now I want to show some automatic environment variables in the build. Whatever. No. Run shell. Okay. Okay, so now I am again in the build environment. Maybe I will make this smaller so you can see also the document too much. Okay. So in the build environment, there are some predefined environment variables. So I already mentioned CC, CXX for the C++ compiler. You have also FC for the Fortran compiler. In all cases, for all platforms, you use GFortran because that's the only Fortran compiler that we have for all the platforms. And there is also ObjC for the Objective-C cross compiler, which is relevant only for macOS. So another thing is that these are the variables for the target platform. Sometimes you need to build something for the native platform because you need to build, I don't know, some native tools to run, some native programs to run during the build. And for that, we have the CC. Is it host? Is it build? So this is the name of the local, like the native C compiler. So the compiler for the Linux Muscle platform. So we have the same for XX build and probably for Fortran. Yeah. Okay, so also this one needs to be updated. So today we will receive hopefully many documentation updates. Instead, these are some variables that you may need to modify during the build. These are not set automatically, at least the first ones are not set automatically. So you may need to change the C flags variable, environment variable for the C compiler or the C++ compiler and so on. And these are other automatic variables that are not they are not used by the build systems, but they can be useful during the build. So prefix is the path of where all the files will be installed. So basically, at the end of the build, everything is inside this directory will be put inside the tarball. So your idea when you build something is that you need to have something into this directory. So in this case, probably it's empty. Oh, it doesn't even exist. Yeah, but you can create the directory and I don't know, you can build the local program and you can install it under prefix /bin. So you build your program and then you move it. If you don't have a build system, you can do this, for example, manually. Yeah, but remember that we also have the environment variables for example, the directory where the libraries will need to be installed or the binaries will be installed. So for example, bindir is a path to the directory where the programs will be installed, which is always equal to prefix /bin. Instead, the libdir environment variable is /lib when you are going to build for Linux, macOS, or FreeBSD, and instead will be prefix /bin for Windows. But the good point of having these variables is that you don't have to care about this difference. So it's always taken care by the environment to set these variables correctly. Also, the environment variable for where the header files are going to be installed. The environment variable for the target, which is sometimes useful if you need to do something which is platform specific. So you say, I need to do this step only when I'm going to build for Windows. So you can, no, sorry, you can do something like this. So target equal contains. So this is basically saying contains min GW, then do something. Otherwise, do something else. So this target environment variable is often very useful to check this, to do these platform dependent steps into the build script. Other useful environment variables are, for example, dlxt, which is the extension of the dynamic library for the target platform. And this is also useful because it is platform dependent. So when you target Windows, will be DLL. When you target macOS, it will be dylib. And when you target the other Unix systems, it will be SO. Similarly, we have ext. So ext, which is the extension of the executables, which is empty for all the Unix systems. Instead will be .x for Windows. So pay attention that in this case, the dot is included because the Unix systems usually don't have any extension for the executable. And yeah, here you can see the list of all the variables that we predefined that can be useful during the build. And here is also a suggestion how to change the compiler for macOS and FreeBSD and use GCC instead of the default LLVM. Again, we use by default GCC for Windows and Linux, and Clang LLVM for FreeBSD and macOS, because these are the default compilers for these systems. And here are also listed some utilities that we provide in the build environment, like a user-friendly patch version of patch, which doesn't mess with the file when the patch fails. So you can this is a syntax similar to patch, with the difference is that you don't need to redirect the path to atomic patch, so it's just an argument. And yes, if the patching fails, the file is preserved. It's not mangled and it's not unreadable. Another useful utility is update configure scripts. Sometimes when you build something that has a very old build system based on configure, it will not be able to recognize, for example, the muzzle C library or the AArch64 triplet. So if you see some errors related to this with configure.sub, I think, not configure.guess, just try to run update configure scripts and try to run again the build. So we provide these scripts to automatically update these scripts, and you don't have to manually download them. Okay, I think this is most of what I wanted to show now. Any other question?
Doesn't look like it.
Yeah, we are sorry for the not too much interactive session, but it would have been very hard to manage all the failures of all the users.
What? Failures? No. There would never be any problems with binary.
Yeah.
All right, guys. Well, that's the end of our prepared content. If you have any issues running Binary Builder and such, please go ahead and open issues, contact us on Slack. Our Binary Builder channel on Slack is actually one of the most active channels in the entire Julia Slack. Well, depending on the time of year, I suppose. So yeah, don't hesitate to reach out. I will be hanging out in this Zoom call for at least the next 40 minutes. So if you want to try something and you want to get interactive feedback now, feel free. But if all the participants leave, then the call will end. So go ahead and have a great rest of the day. And if you have any questions, hit us up.